talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We can attack global warming.
Security.
What are the boundaries of machine learning?
Fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast, and we're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in a billion parallel universes at the same time?
Wow, what a time to be in technology. Welcome to quantum computing. My name is John Azariah. I design QSharp, the language for quantum computing from Microsoft. And this is Dr. Julie Love. Together we're going to talk a little bit about what this whole quantum computing thing is about, and hopefully give you a sense of wonder and inspiration going forward. Thank you.
Hi, I'm Julie Love. I'm one of the business leaders for quantum at Microsoft, and I also have a PhD in quantum physics, so it's awesome to be here with you today. So as we think about quantum, it really represents a total paradigm shift for computing. We can try out on a single piece of hardware all computational paths at once, leading to breakthroughs in all sorts of fields, in environmental problems, energy, healthcare, smart materials, and more. And to do this, we need to do two really hard things. The first is that we need to build an extraordinary piece of hardware that harnesses the power of quantum physics, these magical properties like superposition and entanglement. Next, we need to learn how to program these machines in a dramatically different way, in a way that lets us hear the right answer from all of these computational paths. And at Microsoft, we have a plan to do this, and that's what you're going to hear about from us today. And here at Microsoft, we're focused on the real prize, the real problem, which is solving and helping our customers solve the world's unsolvable problems. But we can only do that if we have technology that scales not just to hundreds or thousands, but maybe millions or billions of qubits. If you think about the journey that we've been on with transistors for the past 50, 60 years, we went from having room-sized computers in the 60s with 13,000 transistors to something like today with our Xbox has 5 billion transistors. And this is no longer considered innovative. This is the expectation. And quantum needs to take the same journey. So you're going to hear about our plans for the quantum computer and how it's architected for scale from day one. So this is Microsoft's strategy for building a quantum computer. I think about it in terms of 3 big pillars. The first is that we're building a comprehensive solution. This requires revolutionary quantum hardware, but it's not just the quantum hardware that's required to build this scalable solution. We do, as you'll see throughout the presentation, in order to maintain the quantum information, we need to put our quantum hardware in an extreme cryogenic environment. So it's this new cryogenic systems, it's classical control systems, it's new runtimes, it's new algorithms, it's new software. And of course, this will all be integrated seamlessly within Azure. Of course, the qubits themselves, the quantum hardware, is critically important. And that leads to my second pillar. It's this, what we call the revolutionary topological approach. This allows us to do computations longer, more efficiently, and with fewer errors. So with these quantum bits, it's really, the error rate really matters. The rate at which, so when they interact with the environment can measure the quantum state, and it destroys the quantum information. And so we have to keep it isolated from the environment. And at Microsoft, we're taking a really different bet on the quantum bits itself, where we encode the information into the material itself, making it much more immune to these errors from the environment. And I think about the qubit itself. The analogy that I like to use is building materials. So you can build a house out of bricks and 2x4s, but those aren't the materials that we use to build a skyscraper. We build skyscrapers out of concrete and steel. Why? Because they scale. And so you think about building a skyscraper, and if you were to use bricks, you have this problem of mortaring it all up and making it tall and immune to environmental effects, winds, earthquakes, but then just the logistics of getting the bricks and storing them and transporting them. And so it's critical that if you're building a solution for scale, you have to have the fundamental building block that scales. So think of our qubits as being made out of steel. And the third pillar is really what makes this all possible. It's about making bold investments in a global team. This is happening at the highest strategic levels of the company. If anyone in this room has read Satya's book, our CEO published a book in the fall called Hit Refresh. And in it, he talked about 3 technologies that are coming beyond the cloud. And he talked about augmented reality, artificial intelligence, and quantum. So we're making bold investments in this space, and we're doing it with a global team. So think about this comprehensive solution and this topological approach to the qubit, brand new physics. We need a really dynamic, diverse set of people, talent, to build this. And we knew that we wouldn't find of all of those people here in Redmond, so we've built this global team, which you'll hear more about. And so now I'm going to hand it back over to John, and he's going to tell us kind of why quantum? Why do we need these powerful machines?
Thank you. So, a small homework problem for you. That number is comprised of 2 prime numbers, and it'd be very, very cool if you could go off and figure out what those were. If you did this a little while ago, that solution would have netted you $700,000. No takers? I guess not. It's probably a good thing that it's hard to solve that problem, because the world's economy is based on RSA at the moment. And computationally difficult problems are what the current approach for encryption is, right? So if you try to do this classically using the brute force approach, taking every number and multiplying it with every other number, it would take you 1 billion years. So if you have some spare time, you might want to get started now. But this turns out to be one interesting problem that is actually trivially easy, at least theoretically, with the quantum approach. So in 1994, a professor from MIT, Peter Shor, came up with an algorithm for factoring numbers using some of the quantum phenomena that are available. And the current estimate we have, when we have enough qubits, is that should actually theoretically take only about 1.5 minutes, give or take, right? This might excite a lot of people just yet, but hold your horses, don't go on shorting Bitcoin and all that right now. That's a difficult problem. The point I'm trying to make is that if you think about the 2048-bit problem and you used 2003's technology, you'd require more than 1 billion years with a cluster of machines to solve that problem. 2018, you'd improve it to the point where it's 1 billion years, but if you look at that graph, it's actually an exponential graph that's moving slowly to the right. And there are limitations, as we're going to find, with how we can use classical computation. And the limitations are going to follow that curve. That curve represents the limit to how much computational power you can get from a classical machine. What we want to do is change the curve completely. And for certain problems, we can. As it turns out, for the problem that I just showed you, factoring those two numbers, with a 1 megahertz quantum computer, it'll probably take you a day. With a 1 gigahertz one, it'll probably take you a minute and a half. This kind of leap in the way in which we are trying to break the limits of computing capability is really what quantum computing is for. Now, quantum computing can't solve every problem with this kind of speed up, but there are certain problems that you'll get this kind of speed up for. And the idea is that we, as a computing community, need to use both the physics, the quantum mechanical phenomena that are available, the algorithms that people have developed, the hardware that we are trying to build, put it all together and try to solve some of the problems that we can solve using the quantum speedups that we get on that bottom blue curve. And if you notice, this makes a lot of problems tractable that were actually completely intractable before. All right? So
Can I ask a question? Are you assuming that the 1,000 whatever qubits are noiseless?
yeah, that's a good question. The question was, are these noiseless qubits? And the answer is yes. We are assuming that all of these are idealized logical qubits, and that they're idealized logical operations as well. So the qubits last forever, and operations take, practical period of time. Sure. Now this machine, Julie mentioned room-sized computers. We still have those. They do a little bit more now than they used to before. This is the fastest supercomputer in the world. It's a TIA Lite. It's in Taiwan. It's an interesting machine. Does a lot of work. It knows how to fully understand the caffeine molecule, which is quite impressive, because that's what drives me on a daily basis, right? So. But that molecule, which is the FemoCo molecule, is part of an interesting little enzyme that lives in nature. And it turns out to be quite useful. We'll come back to that in a bit. But it's actually not capable of actually dealing with the electronic waveforms of that molecule in any tractable time. I mean, we're talking about lifetime of the universe is not enough for that computer to be able to understand and be able to fully comprehend the complexity of the electronic waveforms of that molecule. And that turns out to be very useful. So this molecule, which forms the part of a molecule in a bean plant, is nature's way of making fertilizer, as opposed to the human way of making fertilizer. The human way of making fertilizer is to basically spend 3% of our global energy output into making ammonia using the Bosch-Haber process. And that involves heating ammonia, heating air and water and so on to very, very high temperatures and very, very high pressures. And we make ammonia, which is the single most useful industrial chemical today, which in fact revolutionized the way in which we feed people. It introduced industrialized farming in 1911, right? It's an extremely expensive process, but we actually can't better it even now. This is in fact what we do today. But that molecule, if we could understand that, we might actually change something. We might actually be able to generate ammonia without having to go through the Bosch process. And we can't understand how it works. Now, why is this important? I'm going to let Dr. Feynman tell you a very profound insight about why quantum computing works.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing.
Now, that's a very interesting point. Because you see, nature uses quantum computation. What actually happens in the chemical process, for example, when you use photosynthesis, is a fairly complex interaction of electronic waveforms. And we know what those electronic waveforms are because we can sort of simulate them using linear algebra. But the moment you get to the point where we're talking about large molecules like chlorophyll, or indeed like the Femoco molecule, the maths just becomes too difficult. We can't actually sit down and work out the very large matrix multiplications that it's going to take for us to understand how the chemical reaction actually works. Now, the key insight is this. The chemical reaction is already taking place. It is, in fact, equivalent to this large matrix multiplication that we want to solve. So instead of trying to solve the problem by hand, why can't we flip it around and make the chemical reaction the computation for us? So by treating nature as the computational device and trying to find a way in which we can express the problem in terms of the way in which the chemical reaction works, we can get the quantum devices that are already present in nature, the quantum mechanics of nature, to do the computation for us, to do the difficult computing for us. And in fact, that is the principle behind which we want to build the quantum computer. That's in fact the principle behind which quantum computers are built. Now, this picture comes back to that Femoco molecule that I showed you. You see that nitrogen fixation thing is actually a very, very old process. If you ask farmers from 50 or 100 years ago, they would tell you that rather than put ammonia or urea all over the place, you could just rotate crops. You could plant beans in your field, and that would automatically refertilize the ground. How does that work? Well, in the nodule of the bean plant, in the root of the bean plant, there are some nodules. They're not actually part of the bean plant. They're just nodules that sit on top of the root of the bean plant. And in those nodules, there is a bacterium called Nitrosomas bacter. And it uses an enzyme called nitrogenase. And nitrogenase acts as a chemical knife and breaks the nitrogen-nitrogen bond that you find in the atmosphere and converts nitrogen from the atmosphere and hydrogen from water into ammonia that's in the ground and fixes the nitrogen into the ground. This is happening at room temperature and at atmospheric pressure. So the impact of having the ability for us to understand how that is done so that we can replicate it without having to use the expensive Bosch process would have profound impacts on our economy. It would have profound impacts on the way in which we as a human species interact with the planet. And now we come back to TIA Light, the fastest supercomputer that we can build, and it can't understand the molecule. The molecule is there, it's doing its thing. Nobody told the bean plant that the computation that it's doing is too difficult for us to simulate. But it's doing that. So the trick is to actually be able to use the quantum machine to simulate the natural process so that we understand it better and then be able to come up with a different solution that's based on it. The same thing happens with carbon capture and chlorophyll. The same thing happens with material science. The ability for us to possibly bring a room temperature superconductor that would revolutionize the way in which we transmit energy. Or in fact, using this awesome power of quantum computing to do machine learning. So the scope of the problem that we're trying to solve is phenomenal. It's deeply profound. And what should blow your mind is that each of those problems doesn't require the 5,000 qubits that you need to break RSA. You could get to that with 1/10 of the number of qubits. So while everybody talks about the impact of quantum computing in terms of global economy, I wager that you will get here first and have a much more profound positive impact on the way in which we live and the way in which we interact with the planet before we get to the point where we start destabilizing the economy. Obviously now, This model of thinking is quite different and builds on different building blocks. The building blocks are, of course, quantum mechanics, and Julie is going to here talk about that.
So to give you some insight into how these powerful computers work, I thought I'd talk a little bit about the strange physics behind them. And when I started studying physics, I was fascinated by the way that you could write down a set of equations and really understand the way that the world works in a truly fundamental way. And I love this concept of resonance. I was fascinated by it. The idea that an opera singer could shatter a glass by singing a single note. And by learning enough physics, I got to understand that sound travels as waves. And if the wavelength of sound, or the distance between kind of the squishing and the squashing of the air pressure, if that's the same as the physical dimensions of the glass, then the energy of the sound can be transferred to the glass and shatter the glass. And so this is this resonance phenomenon. So light, of course, also travels as waves. We learned this from Maxwell in the 1850s, and that light travels as a wave of electric and magnetic fields traveling through space at the speed of light. But light also has an alter ego. It can travel like a wave, or in certain experimental situations, it can travel as quantized packets of information. So this is what Einstein figured out about 100 years ago, this wave-particle duality, and we get these quantized bands of light in some experiments. This is the quanta behind quantum mechanics. Now, depending on when you learn chemistry, I was taught this model where you have, this is what the atomic structure looks like, where you have this centralized nucleus and electrons that are whizzing around, kind of like planets orbiting a solar system. Well, now we know this is a pretty simplistic picture. And we owe our modern understanding of atomic structure to this guy. So this is de Broglie, and his name might indicate that his parents were a little indecisive. But he was a PhD student in France, and his professor was Langevin, and he was at university for a few years and hadn't really gotten much done. And he actually had a reputation of being quite lazy. And his supervisor, in an attempt to get him booted out of the university, went to him one day and said, hey, it's time to write your thesis, but just so you know, it's going to be reviewed by Einstein. And so he thought, this is a surefire way to get this guy out of here. And so de Broglie took a step back and he said, okay, well, if that's true, then I better read up on what Einstein's been up to lately. And so he got familiar with this particle-wave duality of light, and he started to wonder if nature was symmetric. So matter, which is, of course, known to be particles, he started to ask the question, does matter also exhibit wave-like properties? And so this is what he proposed in his PhD thesis. He wrote it up. And Einstein was one of his reviewers. And so this is the quote from Einstein's report on de Broglie's thesis. He has lifted a corner of the veil that shrouds the old one. And de Broglie was awarded his PhD in 1924, and this was experimentally demonstrated in 1927. And he won the Nobel Prize for Physics in 1929. Sort of humbling for those of us who also have a PhD, where that's very fast. And so this now is our modern view of electronic structure. And this is where we can start to understand what it means for electrons to take on this wave-like property. And so these are computer simulations of the vibrational modes of the hydrogen atom. And just like the glass that was shattered by the opera singer's voice, it turns out electrons having this wave-like character have different modes that they kind of wobble around in, and this corresponds to different orbital structures or energy levels in the atom. And on this picture where you have a bright lobe, this is where we have a high probability if we were to do a measurement to find an electron. And where it's dark, we have an extremely low probability of measuring an electron. And it's really this wave-like character of quantum objects, like electrons, that allows us to encode and process information in a dramatically different way. So it's like John says, nature is doing this quantum computation already. And so this is very dramatically different than how we process information using classical computers. And so, if you think about going back to today's modern economy, it's all built on computers. And if you open the hood of the computers, of course, you'll find transistors. These transistors are little switches. They're on and off, and we map that as ons and offs to zeros and ones, and this is binary. Quantum bits, on the other hand, or qubits as we call them, because they have this wave-like property, they exist in a superposition state where they can be 0 and 1 at the same time. And the real power of processing information is this way, is when we allow these waves to interact with each other. So imagine if the floor up here were water, a still pool of water. If I were to throw a rock in, a wave would ripple out. And if I were to throw 2 rocks in at the same time, 2 waves would ripple out. And in some cases, those waves, the amplitudes would get bigger as they constructively interfered. And there would be places where the waves had an opposite phase and destructively interfered. And so we can compute using this addition and subtraction that depends on the relative phases of these waves. And it gets a lot more interesting when you have more than 2 that you're throwing in. And this is what gives rise to this massive parallelism. It's the interference of multiple quantum waves. And a well-written, a good quantum algorithm uses this interference in such a way that the answer that we want, the right answer, constructively interferes and the amplitude gets bigger, and all of the wrong answers disappear. They can deconstructively interfere. So we encode information in these waves. And computing with this wave-like nature of particles allows us to do this in a much more compact way. So on the right hand of the screen, I have my quantum register. This is 4 quantum bits, each of which can be 0 or 1. And I can encode, if I had 4 classical bits, each of which could be only 0 or 1, these can be in any one of 16 combinations. But because these quantum bits can be 0 and 1 at the same time, I can encode them in a linear superposition of all of those 16 combinations at the same time. And if I wanted that level of compute power, if I wanted to simulate what's happening on my quantum register with classical computers, I'd need copies for each one of those combinations. So that's how many bits I'd need on the left. And this grows exponentially, the compute power that's stored in that quantum register. Every time I add a bit to the quantum register, I would double the number that I would need on the left to represent that information classically. And so this is similar to this game you might have seen with the chessboard and grains of rice. And so you put 1 grain of rice on the first square, and then on every square you double it. Well, the rest of the picture is not shown because by the time you get to the end of the chessboard, you need 10 to the 19 grains of rice. So to put some numbers against this, if I wanted to simulate the information encoded in 30 qubits, I would need 16 gigs of RAM. When I go up to 40, this is 1,000 times more memory. So this becomes a 16 terabyte workload. When I get up to 50, I'm now reaching the limits of classical compute. This is a 16 petabyte workload. And the data point that I like is if you had 260 quantum bits, so trivial classically, 260, if you wanted to simulate that classically, you would need a computer that has more bits than there are atoms in the known visible universe. And so you can start to get a feel for really why we require this quantum computer. Because classically, as John was saying, these powerful supercomputers, they will never get to this level. We're talking about problems that classical computers will never be able to solve. And with that, I'm going to hand it back over to John, who's going to tell us how we build these extraordinary machines.
Yeah, so that should blow your mind a bit. It does mine. So we come back to the inescapable conclusion that if you want to actually break the 250 qubit limit, you have to basically do things differently. When we started with valves and moved on to transistors, they gave us orders of magnitude in terms of miniaturization, power saving, and so on and so forth, to the point where we have supercomputers in our pockets with our phones. Now we're talking about stuff that is provably beyond the capability of any classical machine that we can build. And so we need to actually lean on different techniques and different technologies. The good thing about it is that we actually know the physics. The physics isn't, we know the physics. The physics is straightforward. We know the maths. The maths is kind of straightforward, right? We can observe phenomena that are not straightforward. We can't really explain entanglement, but we've seen it, and we can depend on it. We can measure it. These are things that are observable and predictable, and this is probably the most famously replicated experiment in modern physics. Nobody understands how it works, but we know what the properties of it are. And now it's time for us to actually exploit these phenomena, exploit these behaviors to give us that kind of improvement that we want. So that's what we're doing. Back in the 1930s, this gentleman predicted that there would be something known as a half electron. Now, it turns out that it's mathematically straightforward to derive this, although physically it kind of boggles the mind that there's such a thing. It turns out that the Majorana fermion is its own antiparticle. So think about a wave that when it meets itself 180 degrees apart, will actually annihilate itself. So it's kind of like that. That interesting particle was only predicted in the 30s. And we had this mathematician come over to Microsoft saying, hey, we can use this to build a quantum computer. And then we had this team go off and actually observe this 6 years ago. And that particle has actually now been seen in the lab. And at breakneck pace, 6 years later, we're actually talking about building a machine with it. So that should give you a sense of the scale at which we're moving to try and build this quantum computer. Now, you might have heard about qubits everywhere, right? IBM's got qubits, and Rigetti's got qubits, and Google's got qubits, and we haven't got a qubit yet. But all qubits are not created equal. The idea that we would actually be hunting for a qubit based on a particle that was only observed 6 years ago borders on the absurd if you don't actually have enormous confidence in the people behind the ones who found the particle and the people who are actually building stuff with it. And the goal that we want is for us to have a very, very high fidelity qubit. So if you look at what we've got with the other qubits, you'll find a large number of qubits with a very high error rate. And the topological qubit that we're shooting for allows us to have qubits that have very low error rate that allows us to scale out. So the point that I'm trying to make here is this. The goal that we want to hit is not just to build any old computer. Our mission is to build the first scalable, enterprise-ready quantum computer on the planet. And we believe that this is the way to build that scalable computer out. We believe that if you don't have a scalable qubit, as in the topological qubit, it's going to take much, much more effort to build the kind of computing capability that we want out of it. So that's the big picture. It's a trifle cold down there at about 15 millikelvin. All the quantum phenomena that Julie talked about, that lives really, really close to absolute zero. It lives in a very isolated environment because a single photon can actually interfere with the quantum state of something and change its behavior. So the engineering challenges of getting something to 15 millikelvin, keeping it isolated, and actually doing the quantum behavior that you want, that's something that is a challenge. But it's only one of the challenges that Microsoft has to face before we build this scalable machine. Relatively warm at around 4 Kelvin, slightly warmer than the temperature of deep space, we have a computer that can actually control the qubit. Now, your normal CMOS doesn't work there, so we've got to come up with a different way of building that computer. And then there's this interesting little engineering challenge of getting a wire, or a few thousand wires, from 4 Kelvin to 15 millikelvin without thermally contaminating the cold space. So the engineering challenge is just below 4 Kelvin. They're at least as hard as building the qubit itself. And that's actually a very essential part of building a scalable, enterprise-ready machine. I don't know about you, but at 300 Kelvin, I'm a trifle cold. I wear a sweater around at that point in time. But once you have the whole machine, you've got to be able to use it. And having a programming model, having a set of libraries, having the ability to actually write software that you can then use the device in order to get a real-world solution to a real-world problem, that's hard too. It's not in the same scale as the other two, but it's still pretty hard. Luckily, that's one area that Microsoft's been kind of good at. We've been in this language building, compiler tooling, software development space for some time now. We know a thing or two about that. So we've put people at every level of this to be able to solve all three solutions at the same time, so that when it comes together, we will have a full-blown, full-stack quantum computer. So just to reiterate, what's it going to take to build a scalable machine? Well, we've got to have the scalable qubit foundation, which is what I told you about, the topological qubit. We need the cryogenic systems that we need to actually control the thing. We have to have some way of actually interfacing with the classical interface, the quantum device with the classical interface. There's obviously a bunch of stuff with error correction, which is far too technical for this audience, because I can't understand it, right? The easy bit is the scalable software stack, because I can understand that. And somehow we got to get this thing so that it lives in an Azure environment and you make it available through Azure. And above all of this, people are still working on the really theoretical problem of what can quantum computing do better than classical computing? How do you make things better? And so the algorithms for this, if you think about Quicksort being developed for classical computing, similar algorithms analogous to those are still being developed for quantum computing. And in some sense, you need all of these to come together in order to make the quantum device works. So our goal is to say, hey, at some point, we will be able to actually get everything working together because of the big picture that Julie talked about earlier in the game. We have bold investments, a global team, a strong vision, and we kind of know what it's going to take to build the most comprehensive solution so that we can build the first truly scalable enterprise quantum computer. And we've been working on this for some time now. We've been working on this. This isn't yesterday's problem. We've been working on this for about 20 years now. Now, this last bit of the talk is really where I come in. This is what I do. We have now built on the software side. Now, we've decided, we've had a discussion at this venue about what is the physics behind everything, what is the global scope of the problem that we're trying to solve. But now let's get into actual, what does quantum computing look like? What are the rules of logic and so on and so forth? And I'm going to try and attempt in the next 10 minutes to give you some idea of how to relate what you know on a daily basis with your classical computing knowledge and how this relates to quantum computing. So let's just take these as axioms for the moment. These three are the most important rules of quantum computing. You have a qubit. A qubit encodes a state, which could be some combination of 0 or 1. You can perform operations on this qubit. All operations have to be reversible, as in, if you perform an operation, there has to be an inverse of it, which you can bring it back to its original state, except for measurement. Measurement is the only thing that you can't bring it back to its original state with. And given an arbitrary state, you can't copy it. So you can't do let A equals B and expect everything to work, because that specific paradigm is forbidden in this model of computing, right? So, the pretty picture. So if you think about a bit, as Julie pointed out, is either a light that's on or off. You can think about it that way. A qubit, on the other hand, is a slightly different beast. Think about a beach ball. So if you had a beach ball, and the 0 state was the North Pole, and the 1 state was the South Pole, then any point on the surface of the beach ball would be a valid state of the qubit. So now it becomes sort of obvious why every operation is reversible, because every time you get to from one state, one point on the beach ball to another point on the beach ball, all you're doing is rotating the beach ball in some way, and you can rotate it back, right? So superposition is obtained by moving away from either the 0 or 1 state to somewhere on the beach ball, and you can rotate from one position to another. And each of those rotations turns out to be, in effect, some form of a matrix multiplication. You can think about it that way. You can't know arbitrarily which value you're at, because there isn't a global sort of polar coordinate system, for example. So you can't just clone the state by looking at the beach ball. And when you measure a point on the beach ball, you only get whether it's 0 or 1 based on some probability. So if you think about what's actually happening, you've represented an infinite sort of space of values in a single qubit, but you can only read one classical bit out of it, because measurement will either give you a 0 or 1. And that's the ball you get to play with for in this quantum world. Don't ask me to show you what that looks like for 2 qubits, because you can't. That's already, that diagram is actually deceptively simple. It is actually a 4-dimensional sphere that has been projected onto 3 dimensions, and then projected onto 2 dimensions, so I can show it to you on that screen there. So, yeah. Yes. So there was a comment here about unitary transformations, and I really don't want to get into linear algebra at this point. So perhaps after the talk, we can have this conversation. But I will show you this. Now you're comfortable with that NOT gate. And what that NOT gate is something that takes a bit that's in the 0 state to the 1 state, or the 1 state to the 0 state. Now, that's really where we stop with electrical engineering. But if the 0 state were actually a vector of 0 and 1, and the 1 state were a vector of 1 and 0, then in fact, that matrix would perform exactly the NOT operation on it, because it would take the 0 vector to a 1 vector, and a 1 vector to a 0 vector. And in some sense, you can represent everything that we've talked about here in terms of that linear algebra operation. And that operation's analog in the quantum world is called the NOT gate, which is represented by X. And it does exactly that. So given an arbitrary vector of alpha and beta, because we're now in superposition, that operation takes it from alpha beta to beta alpha. So you can represent even your known classical computing using these vector matrices if you want to make life a little bit difficult for yourself. But it'll turn out that you'll find that there's a direct analog between what you've got classically and what you have quantumly. And the only difference is the vector, because the vector is not just 0 and 1 anymore. It's actually two complex numbers. So if you look at the kind of operations that you can do, we have a normal proof. I mean, there's a classical proof that says any n-bit operation can be performed with a finite number of n-bit NAND gates. There is an equivalent operation where you can say any operation on n qubits can be performed with a finite number of operations. Now, each of those operations is, in fact, a unitary transform. And it's really a matrix multiplication. So these building blocks, you can kind of take for granted when you start moving in the quantum space. It's just that they're a little bit more complex than the building blocks that you have with the classical world. But there's actually quite a fair bit of correlation between the two. So for example, you can have De Morgan's laws to reduce your expressions from a classical point of view. And in quantum computing, those laws are actually linear algebra laws. So the math is a little more complex than in classical. That's really what it boils down to. So you remember I told you that you can't actually copy state? It turns out that it's quite useful to be able to move state. And this is really the principle of teleportation. The idea that you can take an arbitrary state that you have on the one side and move it to some other qubit. So if you have an arbitrary state, if you have a qubit in one state, you can make another qubit in the same state. But by doing so, you necessarily have to destroy the state of the original qubit. So you can't just copy the state across, but you can move it. That picture on the left is traditionally how quantum physicists talk about computation. It should remind you of a circuit, because that's really what it is. And those gates that you see there are really transformations that take the state of the qubit from one state to another, which is really what gates do. If you really think about how you draw out a digital circuit and you look at the values of the bits as you go through, you get the same effect. So in some sense, you can think of a NOT gate exactly as I pointed out earlier as a kind of transform. And indeed, that's really what is being shown in that circuit over there. Now, there's a problem with that. There's a problem with that because the circuit can't operate on an arbitrary set of qubits. For every qubit that is there in your diagram, you have to have a line in there. So you can't say, oh, I'll write a general purpose algorithm or a general purpose circuit that takes n gates. You can't do that. And that's a limitation, I think. So that's part of the reason why we talked about programming in your own language, where you can write a program which can subsume and represent every circuit there is and strictly represent more than circuits can represent, because I can now take a function and have it take an arbitrary set of qubits. So to be able to do that enriches the way in which we think about it. So this gives you an idea of what Q-sharp looks like. It's really representing the equivalent code to that circuit over there. So when we designed the language, we brought in influences from all the languages we knew about. There's a strong functional concept. The functional languages played a very big role in influencing the concepts that we have. And we kept the syntax simple and familiar. And we introduced a type system, and we made it so that we were able to represent quantum-specific concepts that you could not represent in traditional languages. And this is useful and important, because if you don't do that and you take the traditional or the current state of the art, which is to take a language like Python and slap a couple of libraries on top of it, you won't be able to do the kind of thing that we'll be able to do here. As in, you won't be able to reason over the kind of programs, be able to resynthesize portions of the program, and so on. And fundamentally, this is what makes Q-Sharp more powerful than the stuff that's out there. Indeed, the proof that Q-Sharp is powerful is present in our library system. I'll show you in a few minutes. I'll show you the libraries that have been built by the quantum researchers that work on our team. We already have the building blocks, the algorithms, and the libraries for using, for anyone to general purpose use at this point. And this can't be done if you were just writing code against a host language. So being able to express these quantum constructs in your own language succinctly and correctly gives us the flexibility and the ability to be able to even publish a language or two. Now, what does it mean to you? How do you actually get started with quantum computing? Well, the way we should think about quantum computers is actually exactly the way we talked about earlier, as in there is a physical process somewhere that is going to do the difficult computing for you. And that's kind of like a coprocessor. So you write code in a host language, and when you want to solve the part that is hard, you write the hard part in the language of the quantum device, and you let the quantum device act as a coprocessor for you. So when you want to develop now, we have a simulator. You write the host program in whatever language you like. You make use of the libraries in Q-Sharp. You make use of code in Q-Sharp. And then the simulator, or the simulator in Azure, keeps track of classical matrices. So that 16 terabyte limit, or the 16 gigabyte limit that Julie talked about earlier, you run into that at this point. So you basically have this large matrix, and your computer can do the matrix multiplication for you. So you have a limited number of qubits that you can actually simulate. Of course, once you get the quantum hardware, it's going to give you a lot more in terms of what it can do. And it's not going to store simulated values. It's going to store stuff in the natural physical state. And you don't get to see that physical state, but it's storing it at infinite precision, and you get a much bigger sort of space that you can work with based on the number of qubits that you have. But if you notice, the stuff that you write here in terms of the host program and the Q-Sharp code, that retains its value. So you can write stuff that runs against the simulator today, and when the quantum hardware becomes available, all the investment that you put in here can simply be run against the quantum device. So that's kind of the logical computing model that we have. I'm going to skip this slide because this talks about why having our own language is better. And I'm going to talk about that one in the demo. So what we have today in the Quantum Development Kit is actually a full-blown simulator that you can use. You can simulate up to about 30 qubits or so on your local machine. You can simulate 40 qubits or so in Azure, but it will take you time and money. And then we have special purpose simulators that can actually do things like just count the number of qubits you would need, which is something that's very useful because if you're improving your algorithm, you now have a basis on which you can actually run against, and it tells you that this tweak to your algorithm reduced the number of qubits you needed by 10%. It's kind of like runtime profiling on a traditional machine. And that sort of is the big picture of what the Quantum Development Kit is. So you can now go off and get the Quantum Development Kit and actually play with it. What I'm going to do is switch over and give you a quick demo. Now this is everybody's favorite programming tool, I think. It's mine anyway. So it's Visual Studio. It's running Q-Sharp and C#. And this is going to teleport two classical bits. So if you go ahead and look at this, this is a traditional C# program. And I'm going to teleport the value true and the value false in quick succession from one qubit to another, right? So this is exactly the same picture that you saw earlier where you had 3 qubits and you transfer the state of one qubit to another. But the cool thing about it is that I can now put a breakpoint in my Q# code. So this thing, which looks like C#, is actually Q#. You get code coloring and everything. And I'm going to go ahead and start. And if you have keen eyesight, you'll notice that the value of flag is true. And that's because I sent in true first at this point. So I'm now actually simulating this code running in Q# against a simulator, and I can step through the code and have it run. So I can go ahead and run that. And this time, the value of flag is false, because if you remember, we wanted to simulate true first and then false after. So it's like developing in a traditional programming language using the quantum concepts that are there. And indeed, you'll see that we've teleported true and false successfully. So this kit is available today. You can go off and go ahead and use it. There's, in fact, a whole bunch of libraries and things that are available. So if you just go down to the microsoft.com/quantum, you'll find this page. You can get started with the quantum development kit. You can download it, sign up for a newsletter or whatever it is. And this is the library set that's available. It's completely open source. It's on GitHub. We have full-blown documentation that's available that gives you the ability to go off and learn things as well. So there's a reference on the Q# programming language. There's comprehensive reference on the various algorithms that are available. And all of this will basically ease your jump into the cold water of quantum computing. But it's actually a good deal of fun. And once we get started with using this, you think about even classical programs differently. In fact, there is a whole slew of algorithms that are classical algorithms that have been inspired by quantum optimized concepts. They're optimized from the concepts that you get from quantum computing. So with that, I'm going to switch back to the PowerPoint. If you want to see more about this, you can. I'm going to give you. There are going to be 2 talks today at the theater downstairs. So come by and I'll dive into this in much more detail. So those are the links if you want to take a good picture of this thing. And you can go ahead and contribute to GitHub. We accept pull requests at the moment. We have the quantum development kit for you to use. And we really want you to get started with this. The idea is that the problem space is huge. The opportunity is just beginning. And I think we're at the forefront of having the most exciting development environment that you can start sinking your teeth into and learning to solve problems a different way. Where are we at? Do you want to do this? No. Yeah, I think we'll open questions. Yeah, so I think we're done with the talk itself. We have about 15 minutes for questions. So if there's a mic, I think we can get them.
Mics around the room.
Yeah. Thanks very much.
Thank you. We'll put that back to the room.
Question?
Yeah.
The problems that would get solved with quantum computing, would the developer need to be, we're going to have to know a lot about algorithms, solutions, and a lot more than what we typically do now. Do we need to go back and get a physics degree? A lot more math? It seems like there's a little bit more than the quantum Q#. It seems like you would need a lot more algorithm background. Comment?
Well, I don't have a PhD in physics. Maybe I'll let Julie handle this one.
Yeah, well, so what I would say is that our aim with Q-Sharp and then QDK is that people can learn how to program like a quantum physicist, but we don't think you need to be a quantum physicist to do it. And the idea is that why we've built all of the libraries and how we've architected the code is such that you can program up at a higher level of abstraction. So you're not sitting down there kind of controlling individual gates and doing that, which you can. You can do that in this programming environment. But you can also program at a higher abstraction level using the libraries and call these functions. And so, I think it is about shifting your mindset. And one of our researchers, he had this question of, is quantum computing hard? And he said, well, no, it's just linear algebra. And you just do matrix multiplication. At some point, these matrices get too large, and then you need the quantum computer. And then he said, well, yes, it is hard, because you have to totally abandon your classical worldview. But we'll just skip that part for now. So, you want to add anything?
No, I think it's a brilliant question, actually. I think the kind of problems that quantum computers will solve will require people who have understanding of the kind of how to express the problems in the first place. So if you're going to solve a quantum chemistry simulation type problem, you will need some background in the quantum chemistry piece. But if you're going to talk about using algorithms like Shor's algorithm, factoring to do other things, or using machine learning library pieces to do certain things, then it's just the domain that you need to understand. And there's probably a bit there that talks about how the domain translates into the quantum building blocks that you'll need to solve the problem in that domain. So it's certainly not going to come for free, but it's certainly not, I don't believe that it's something that's going to require you to understand both the domain and the quantum mechanics in order to make it work. So the joke is now that you only need one PhD to do something, not two. So, yeah.
Okay. So my question is, when you showed the sample code for Q-Sharp, it seemed like there was a lot of manipulating individual gates. Does Q-Sharp already have more levels of abstraction, and where do you see this abstraction in the future?
That's a brilliant question. Yes. So the question is, do we have? Well, I don't need to repeat the question. You've heard it. So yes, I mean that's where the libraries come in. We have basically higher levels of abstraction and more complex algorithms that you can actually use as building blocks that you can basically just run with a large number of qubits in a register, for example. So that's already there. There are examples in the libraries. Go ahead and look at those. But for a demo, especially for someone who is only beginning to do quantum programming like myself, having just the teleport, you need to have those are single gate operations. So you're going to need those. Yeah. Next.
There was a mathematician out of Hebrew University, I think, and I thought it was last year. He claimed that he had proved that the noise on a quantum computer goes up so much more rapidly than the number of bits that you really couldn't build a useful quantum computer. In other words, you couldn't build one with more qubits than could be simulated in a supercomputer. Like, I think IBM just announced they simulated 56 bits. Something like this. I'm just curious if you guys have heard of this. I'm sorry, I can't remember the mathematician's name, but if you had an answer for this. Kilgalai? Kilgalai, is that the Kilgalai? Yeah. So just curious if you guys have had any opinion about that. You're looking at me like I'm crazy, so that's probably.
So I haven't read this particular one. It does sound familiar, but the error rate is critical, and I think if you have noisy qubits, the error correction that you have to do scales non-linearly with this error rate, and so that's
you're just
critical.
Introducing more errors as you add more.
Exactly, and if you're getting into it and looking at the different quantum systems, a lot of times you'll see the 1 qubit gate. So John talked about 1 qubit gate and 2 qubit gates. It's the 2 qubit gate that's harder, and so that usually has a worse error rate. And then, as you saw in that picture where we showed the inside of one of these cryostats, these dilution refrigerators. Doing that error correction, that's a huge computational challenge.
Right.
And so that's why we're building that powerful computer that sits within the fridge, so it doesn't, we call it the fridge, so it doesn't introduce more noise into that. But that's why it's critically important. So if you have something like a 10 to the minus 2 error rate, and the error rate in the quantum computer is the probability in any compute time step that you get an error. If you have a 10 to the minus 2 error rate, the current protocols for error correction say that you need 10,000 physical qubits to have a logical qubit that could solve something like this FOMOCO.
Right.
And so that's why, I mean, that's truly why we're investing in this topological phase of matter to build our qubits out of. So you bring down the resource count substantially. So we're targeting 10 to the minus 6 error rate.
So you're absolutely right in that there is a threshold at which point a noisy qubit with a certain level of noise cannot be error corrected beyond even with a very large number of qubits.
Right.
I think the point you're making is exactly that. We agree that that's actually the case. However, the qubit that we're talking about building has demonstrably better numbers than that. And so we're pinning our hope that when that qubit becomes available, we will breach the threshold of that and be able to get to the point where we're not in that dead zone anymore.
Fine to that, yeah.
Yep.
Great. Thanks a lot.
Going back to your comment that the real challenge is below 4 Kelvin, has anyone suggested building those computers like in deep space or at least out in the outer space beyond the cloud?
It's really, really hard to get those long wires working, you know?
Well, you can communicate, just like you communicate with satellites, right? But your computational, yeah, exactly. Your computational facility is sitting in the space.
Yeah.
You don't need to cool it.
So a size of a grain of pepper is about 1 picosecond, right? That's how fast information can travel. Now, if the qubit's going to last for a millionth of a second, you've got to get your signal in there, get it to actually do its thing, and come back. That's a lot of pepper.
No. But you only send the statement of the problem or your code there. The computation happens beyond the cloud, and then the result is sent back. So you don't need to trace every...
But basically what we're talking about is that the environment, I don't think putting it in deep space is going to appreciably change your noise profile. In fact, your background radiation is going to be much worse.
You can protect against that.
No.
Well, and the classical computer that we're building inside sits a little bit warmer than deep space, but our quantum hardware sits down at 15 millikelvin, so it's 100 times colder than deep space.
Yeah.
And so that's where we have to worry about keeping everything cold and getting signals in. So the 4 Kelvin stuff is relatively easy to get to.
Yeah.
But my second part of the question is Microsoft really trying to build the hardware, or you relying on somebody else building it and you're just building the compiler?
We're building the hardware.
We're building the hardware.
Yep. Okay. So I talked about this global team. We have physicists in Copenhagen and Delft that are building the quantum hardware. And we're building everything you saw up in that chart. So
right. You saw Charlie talk about it. So Charlie Marcus, who was actually one of the people who spoke in that video, is one of the people who are actually building the thing that runs at 15 millikelvin.
Hello. One of your slides, you talked about the libraries in the C#. Now, today there is offer of our language in Visual Studio 2017, where it's possible you install libraries in Visual Studio. But in that case, the search for the packages are in a directory called C-Run that is from Microsoft. I would like to know how you work with packages and libraries in the case of C#. Do you have some directory that's property from Microsoft or some directory that is open in that case?
Excuse me. So the libraries are in Q#. If I understand your question correctly, you want to know how the libraries will be retargeted against different devices?
Yeah, how are you working with these libraries? You install or you search these in some directory?
You just install the quantum development kit. It brings the libraries down, or you can get the libraries down from GitHub and just use them. So you can use them as part of your project, basically.
Okay, thank you.
All right.
Hi, so I'm a dumb developer. When I try out F#, I can conceptualize something that's useful and have a goal to strive for. when I installed the QSharp package, once I learn the syntax, how do I know what to strive for as a dumb developer with no PhDs? I mean, how do I know I'm actually doing something useful, or how can I get to the point where I can start conceptualizing something that's useful?
So this is a really interesting one. So for a very long time, I was probably the only language designer on the planet that wasn't qualified to write a program in the language I designed. Right? So I empathize with your point because I understand what you're saying. Right? I get that. Now, F# is a brilliant language, one of my favorite languages on the planet, almost bar none. But it's a general purpose language. Right? Q# is not a general purpose language. It may be Turing complete, but it's not general purpose. You want to use it to solve problems that basically use quantum concepts. So there is a learning curve in getting the quantum concepts in place and then being able to use those to do certain things. And so my recommendation is you'll need to actually take some level of information on quantum programming itself, and then you'll find that Q# is a lot easier to express your quantum programs than what else is out there at the moment.
Do those resources exist online at this point, or is that
Yeah,
something I
there
can
are
find with
EDX
these
courses.
links?
There's an EDX course currently being presented from MIT with Peter Shor, the guy who actually came up with the algorithm, and Isaac Chuang, I think. And you can take that course. It's actually quite a very useful course to take. And once you start doing the homework, you'll realize that writing the thing down in Q# is actually a lot easier to do than the traditional way of doing it.
And we also find, we get feedback from developers all the time that they find actually just the documentation that we've provided within the QDK and Q# is really helpful to go up that learning curve.
But in terms of motivation of what you can expect to do, you can expect to learn a lot of quantum programming, and then you'll have to get creative in how to actually use it to build something with it. But because it's a domain-specific thing, it's not like you can go off and write Tetris, which is what you can do with F#, right? Yeah.
Thank you.
Hi, quick question. Has Microsoft any interest in developing hardware for QKD for quantum cryptography?
Sorry, I didn't get that
I didn't
question.
catch the end of it.
Sorry. Okay, so has Microsoft any interest in building hardware for QKD quantum cryptography?
Quantum cryptography?
Cryptography. Quantum cryptography, like the BB84 protocol for KX.
Post-quantum crypto.
Oh, no, actually, well, similar to that, but the actual quantum protocols.
No, I think we're just trying to build the qubit first, and then we'll worry about the rest of it.
Okay.
But
Well,
there are teams that are building post-quantum crypto libraries for use in their current classical machines. But in terms of the actual quantum solutions at the moment, we're focusing on from the qubit side building the qubit, from the the cryogenic side building the machine, and from the algorithm side we have a variety of applications that we're looking at, but not the crypto one, because it's not likely to be done with the number of qubits that we're likely to get soon.
Okay, thank you.
We have one more question.
This is just a quick question. So I saw earlier that you are encountering a lot of problems with the quantum computer itself, right? So I'd like to know, do you have a specific roadmap, or do you have a roadmap for the quantum development?
I'll let you handle that one. Roadmap.
Roadmap for the quantum computer?
Yeah, I mean like a roadmap, like what are, like, do you have a target year to have the first quantum computer really working?
So what we've started to say publicly is that we'll have our first qubit this year based on this new phase of matter. And we expect that we'll have a commercially relevant system within 5 years. And so our bar is really high for that. This is not sort of a demonstrator or a toy machine. This is something that's solving real problems for our customers.
Thank you.
Yes, it's already available. Go
online.
download the QDK. One more question.
Actually, my question related to the previous one. Quantum approach actually kills all classical cryptography. Discrete algorithm function problem becomes solvable. So what is alternative?
I'm sorry, I didn't get the question. What?
what is alternative for classical cryptography?
What's the alternative? Oh, post-quantum crypto. It's a real thing. It's not fiction. We have post-quantum crypto already.
And you don't need a quantum computer to have post-quantum crypto. So we've been working with the National Institute of Standards and Technology to develop new protocols, and they're actually available today that you can get started with.
Thank you.
Well, thank you very much.
Thank you.
Yes.